Let's Boltzmann Q&A question number 1. What is the distribution function f? So we are studying the Boltzmann transport equation, which is the differential equation on the distribution f that has an advection operator that looks like this, and a collision operator, which is a function of the distribution function twice. So this distribution function is a particle distribution function, single particle distribution function. So imagine we have a particle and we call this particle Neil. Say this particle has a name, so it is a distinct particle, and we call it Neil Armstrong. So the distribution function now is defined by an integral over a volume, say, call this volume A, and the integral over the volume A and over the velocity space xi of the distribution function, integrated over all velocities over the entire space, over the space R. This is the probability to find Neil Armstrong in this volume A. So Neil Armstrong, of course, is not alone. There could also be a different particle. Let's say this one, and this could, for example, be Nano Muscuri. So there are two particles, and the distribution function here tells us now whether the particle A, or Neil Armstrong, is in this volume or is outside of this volume. So this gives us the probability of finding this. So in the collision operator, we need two distribution functions. So the particle itself and another particle meeting it. For example, the particle Neil Armstrong meeting the particle Nana Muscuri. Now, since the particles are non-distinguishable, they both have the same distribution function. So it's important, we are looking for a distribution function that the probability of finding one particle, one specific particle in this volume. However, all the other particles, because they are non-distinguishable, have the same distribution function. So the distribution function is normalized. We look at it as if we integrate over the entire space f, the velocity, and the space. So, and with this being the universe, the entire universe, then this gives us 1. So the meaning of this is that the probability to find a particle with the only condition that the particle exists somewhere in the universe at any speed is 1. So this is actually how the distribution function is defined. And from this, you can also deduce the unit of the distribution function. So its dimensions, f. The dimension of this must be the number of particles, which is no unit, divided by what we integrate over. So we integrate over 3 directions in velocity. So we have velocity to the power of 3, and we integrate over 3 directions in space. So this is space, so meter in power of 3. So far so good and everything clear. Enters the ether theorem. So ether being defined as the integral over the entire universe over all speeds over the distribution f, and the logarithm of f dxc dr. So now here we actually have a small problem, namely that we take the logarithm of f, and f is supposed to be a quantity that has a unit, and of course we cannot take a logarithm of anything with a unit. Now this is something that is usually ignored in this field, which is probably not a good idea, but it is something that is related to the fact that this here is linear, and we can always scale f with respect to an arbitrary constant. If you think about it, that the probability is defined only for f, or f is defined such that the probability of finding it in the universe somewhere is 1, then finding it in any space much smaller than the entire universe would be a very, very small number indeed, and it is. So in actual calculations, we would rather scale f to a different value and ignore this usual definition. So in order to repair our ether theorem here, what we can do is we can introduce a constant c, and everything this constant has to fulfill other than this constant is that it has the units s by the power of 3 and m by the power of 6, such that actually we can take the logarithm of this without making it mathematically or physically inconsistent. Now, what does this mean for the definition of the moments? So maybe in the full lecture I was not completely consistent on this. So we have something that is indeed a density that we call rho, and this is a function of space and time, and it's integrated only over the velocity space, and this is the integration over the entire velocity space dxc. So now this thing will have now the units number of particles per meter cube. So we can also have the density in terms of mass density. What we would have to do then is we have to multiply this by the mass of a single particle, and in this case the new definition of rho would be kilograms by meter square. Actually, for the velocity, it doesn't matter which one we are using, because we are multiplying. We are dividing by the density again. So velocity is u rt. So this u of r and t. So it's a function of space and time, because we integrate again only over the velocity space, and we multiply this by xi, the particle velocity, and divide by rho, r, and t. So this is a pointwise normalization and integrated over xi. And now for the temperature, in order to be to have it consistent in units, temperature T, we actually have to include the factor m divided by the Boltzmann constant. So m is the mass of one particle divided by the Boltzmann constant. And we also have a 3 here. And this goes into xi minus u, this square. So the square of a vector is, of course, the scalar product with itself. And this again normalized by rho r t, and this integrated over xi. So this is how we are using, so what I forgot is the most important thing, namely the distribution f. So this is the use of the distribution function being defined by its integral over space and velocity space, being the probability of finding it in a particular volume. So that's all for this question. Students enrolled in the course Introduction to Lattice Boltzmann Method at the TU Braunschweig can post further questions in the messenger. See you next time.